I'm going to talk about the link fault tolerant routing algorithm in mirrored K-Ary entry interconnection network. Here is a version of this, and mirror K-Ary entry has been proposed, and it has a lower hardware cost than traditional fat tree and has a shorter packet latency than traditional fat tree. And also, as a scale of count becomes large, the possibility of failure increases. Switch faulty tolerance has been discussed, and we will give a 3-link faulty tolerant routing algorithm for the count and also evaluate their performance through some simulations. Okay, first we will talk about the indicators of the switch. The indicator of the switch, we divide the group to the 0 group and the 1 group, and indicates either use 0 or 1. And L indicates the label. Here's label. The label as well is belongs to 0 to the n-2. And the D n-2 to the D0 as well is belongs to the 0 to the k-1, and the D means switch ID. Okay, and here the indicates of the links. The link also their G and the L means the group and the label respectively, and D also means switch ID. And here we have P in this links, and the P means link ID. The P also belongs to the 0 to k-1. The C means the node ID, the C n-1 means the node ID, and the C-2 to the C0 it means the switch ID. We can know that the C n-2 to the C0 it means node links to the switch's ID. We also call if the node is the source node, we call the switch as a source switch. If the node is a destination node, we call the switch as a destination switch. Okay, here is the count 3 figures as shown in this. There has all the switches ID and some of the node ID and some of the link ID. The switch ID and the link and the node ID is simple, so I won't explain it. But the link ID, we need to notice that between the group 0 to the group 1, here's the link ID is indicates as 1 to that means the 1 means the group ID. The group ID will use 1 and the label ID will use the n-1. Here is the count 33, so the label ID is 2. We won't use the n-1 in other links, but in the in the group 1 to the group 0, we will use it. And okay, here's a connection. Here's an example of the connections. A switch like this will connect to another switch like this, and we can know from the LID, the label ID. The L means the lower level, and it connects to a upper level like this, and in this case, where the link is like this, and the link it doesn't change the group ID, so we will use group IDG, and then the label ID will use our label ID, so we use L+1. And in this case, we can notice that the star mark in here means the no kill elements is well from the 0 to k-1, and the DL will be changed to the no kill the star mark. And in another case is that the group ID has been changed, the G has been changed, and in this case the links we will use that the group ID will be the 1, and the label ID we will use L+1. Also, in this case, we can use the n-1 indicate the label. But in this case, we will learn that in the upper level, the L will be equals to the n-2, and also the link ID will be the n-1. Okay, here is another connection of the node. In this example, the node ID is indicated as this, and it will be connected to the switch like this. The switch connects to the node must be the level 0 switch, and also the link's ID will be indicated as this. It use the switch ID, and the Cn-1 it means the link ID. Here is the routing algorithm of the argument. It imports the packet like this and indicates my switch ID and destination node ID like this. Well, in the first case is that W and the T in different groups, it will be sent the packet to the TLW plus port. It will increase in the label and will it to the upper label. In another case, we can learn that the GW will be equals to the GT. So the W and T in the same group. If the W and T in the same group, it will be the my switch will be will find a path to the nearest comment emitter. We use NCA indicates that, and the my switch will increase in the level to the TLW plus port. When it reaches the NCA, it will find a way to the destination node like this, where it sends to the destination switch, and the destination switch links to the destination node. And finally, the routing algorithm has been finished like this. Okay, here is the algorithm of the fault tolerant. The first one is the go neighbor switch. We can know from the figure that the red dot links means faulty links. It won't be able to find a path where this link. While this link is a faulty link, and my switch is 0100, and the destination switch is 1000. In the routine in the shortest path, we can know that the 0100 will be linked to the 1100, but it cannot be used used to the 1100 in this path. So we can use some other we can use other links to the 1000, like the yellow links or the green links. Okay, and another algorithm of the fault tolerant is go down level. Go down level in this figure, we can notice that the 0100 is the my switch ID, and the destination switch is 0000, and the link from the 0100 to the 000 is a faulty link, and we have some other paths to the 000 to advance the faulty, just like the yellow links and the purple links. Okay, here is the third algorithm. We call that as the externs. The my switch ID is 0100, and the destination switch ID is 1000. And also we can see that the red dot link in here, it cannot be used. And if we use the go neighbor switch, we use the path like this or this. We cannot, the go neighbor switch cannot be linked to the destination switch in this case. So, well, in this case, we can use another algorithm, the externs, to the destination switch like this. And the yellow links and purple links show some other paths we can get to the destination switch like this. Okay, we have talked about the go neighbor switch and the extern switch, and here the algorithm 2 means how does the go neighbor switch and externs works together. And we can see in this algorithm, here is my switch and the destination nodes. Well, if the links is faulty links, we will send the packet to WN via the L. The WN means the neighbor switch ID. So here is the go neighbor switch algorithm. And whilst the L is faulty links too, that means the go neighbor switch cannot find a path to the destination node. So we will use the externs algorithm to find another path to the destination node. And also here is if the L is faulty links too, the routing will be false. Externs cannot find a path to. Of course, while the externs can find a path to the n t lw minus n minus 2 in this case. And this indicates the switch of this. In this case, the 1020, 1020, it means the means of this, quite complicated, and we will send the packet to the TLW plus of the in another group. In this case, it means the 0111. And while it sends to it will and also it will be sent to the TLW plus. In this case, TLW plus means this or this switch. And finally, this case is about go neighbor switch. If the go neighbor switch can be used, it will be used the go neighbor switch algorithm to the destination node like this. And finally is the simulation and future works. When we first talk about simulation, we use the simulation evaluate the average packet latency. We will show this later. And we simulate the network in a Micount 33 with 135 links. For all the algorithms can be effective in a larger scale network of that. And we test all the algorithms for the 100,000 times. And the source destination nodes and 40 links are assigned randomly. And one figure is used for the simulation of all algorithms. Here is the performance. The performance of the three algorithms. We can know the algorithm indicates in the different color of the and different marks. In the horizontal axis, it means the link faulty rate from the 0 to the 100%. In the vertical axis, it means the successful routing radius is from 0 to 100. We can know all the algorithms has improved the successful routing radius. Go neighbor switch and externs can use together in this case. Here is the average path length. Also, the horizontal axis means the link faulty rate is from 0 to 100%. And in the vertical axis is the average path length from 0 to the 4.5. We can know from the figure that the higher performance algorithm will have the longer routing path like this. And next, we show the performance of the algorithm. And in the horizontal axis is the number of 40 links is from 0 to 20. And next is the average path length of the number 40 links from 0 to 20. Okay, finally the conclusion. We have talked about it in the motivation, and in the future research, we may developing a new link fault tolerant algorithm of high performance and evaluating the performance of algorithm for both switch and link fault tolerant in Micount. Okay, that's all. Thank you.